Hi, I'm Jennifer Bowman. I work at the Voinovich School of Leadership and Public Affairs. I'm our senior project manager here. And today, Natalie Cruz is going to join me in presenting on how groundwater works. This presentation is part of a larger funded project through Ohio University from the Department of Energy. We are focusing on the groundwater modeling tasks that we specifically worked on over the last 3 years. And today we're going to talk about the basic background of groundwater and how that ties into the work that we did at ports in terms of modeling groundwater and the implications for the cleanup and repurposing of the port's site. Our presentation is focused on really the background of groundwater. We're going to look at the interaction of surface and subsurface connections with regards to groundwater, groundwater plumes, modeling, types of remedial action that's taken when we have groundwater plumes or groundwater contamination in the natural geologies, and a brief look at applications of how this work that we did at the ports plant with regards to modeling groundwater, what the applications are into the real world. Okay, so first we're going to talk, when we talk about groundwater, we're going to start with the water cycle. So the water cycle shown here is powered by the sun. This is showing the continuous movement of water through the earth. So starting in the ocean, water would travel through evaporation up through the air. Condensation happens, collection into clouds. This is moved through wind over to the land. This will fall back down in the form of precipitation, rain, snowfall. When this precipitation falls onto the ground, we have what's called surface runoff, infiltration, and this is how our groundwater gets recharged. So through infiltration, the water percolates down through the soil layers and down into our groundwater layer. That groundwater then flows through the geologic strata and emerges back into what we see here as the streams or back into the ocean. You can see a full cycle. Now on the land, we also have exchange of water vapor from our plants to the atmosphere through evapotranspiration. Okay, so the distribution of Earth's water, we have 333 million cubic miles of water on the Earth. Now this mass volume of water remains constant, but the partitioning of that water into these different major reservoirs, being ice or fresh water, groundwater, changes based on climatic variations as well as the physical processes of evaporation, infiltration, precipitation. So when we look at the distribution of Earth's water, you can see that 97% of our water is saline. This is in the oceans, leaving 3% to be fresh water. If you take that, just that 3% fresh water and look at the distribution of just the fresh water, you can see most of that is held up in ice and glaciers. 30% of that fresh water is groundwater. So you can see groundwater is a pretty important resource in the overall scheme of just our very small portion of fresh water. And then surface water is even smaller than that, 0.3% surface water, and that's in our, most of it's in our lakes, rivers, swamps. Okay, so let's talk about anthropogenic groundwater pollution sources. In this diagram, you can see landfills, you can see farms, tanks from storage of petroleum products, gas stations, these sort of things. All of these anthropogenic uses on the surface have a potential to contaminate our groundwater sources through leaky pipes, leaky tanks. This has the ability for leaching potentially harmful chemicals down through our water table, down through our soils and into our water table. So chemicals behave differently once they reach the water table. We have some chemicals that are lighter than water. You can see this in the diagram. That would be similar to like gasoline. These would be considered floaters, or L-naples. These are light non-aqueous phase liquids or floaters. And we have chemicals that are denser than water, and we call those sinkers. These are also called D-naples, dense non-aqueous phase liquids. And then you also have the bottom diagram that shows when chemicals are similar in density to water, they tend to just mix at the same rate and the direction that the groundwater is flowing. So we're going to talk about porosity now. Porosity of geologic layers depends on the type of rock. Sand and gravels tend to have higher porosity, while shales and limestones have lower porosities. Higher porosity rocks don't necessarily transmit water well. This depends on the connection of the pores defined by the permeability. So permeability is dictated by the connection of those pores. So, for instance, clays have low permeability, but they have high porosity. So like a clay in the presence of water tends to swell and can hold a lot of water. So it has very high porosity, but it doesn't allow water to move through it, through those pores, meaning it has very low permeability. So clays often are an impermeable layer, a low hydraulic conductivity layer within our natural geology. Whereas a sandstone or a gravel matrix have more pore spaces and better connection of those pore spaces, meaning they have higher hydraulic conductivity, higher permeability, higher porosity. Sometimes you can have sands and gravels that are poorly sorted, where all the pore spaces between them become cemented and packed in, and then that permeability and porosity would be lower. Okay, so now we're going to talk about a couple different factors that lend to understanding the direction of groundwater flow. So we're going to talk about strike and dip. So not all rock layers are flat, and especially not here in southeast Ohio. Our geologic layers dip to the southeast at about 30 feet per mile. So generally water flows downhill, and so the direction that those strata align with, that's also the direction of the regional groundwater. You'll see that groundwater is, the flow and direction of groundwater is also dependent on specific and localized changes in the geology, as well as the connection to the surface hydrology. But regionally speaking, groundwater flows in the direction of the geologic dip, which in our case is to the southeast. So at ports, we have two very different geologic structures. We have a lower consolidated sedimentary structure, and then an upper unconsolidated fluvial and lacustrine sedimentary structure. That area where ports is situated is called it's from the ancient Taze River Valley system. That's the old Portsmouth River channel. And so that geologic material that is laid in the middle there, sort of say, is the old riverbed. You can kind of see the shape there. You see the Scioto River, and then the consolidated layers of the hills there, kind of like a basin of sediment that's where ports is situated right on top of. We can take a closer look at the next slide here, where we see the geologic layers dipping to the southeast. That's our consolidated regional geology layers. And then you can see the basin there that's filled in with that lacustrine lake sediments from the old Portsmouth River channel. Now when you look at those layers in the middle, you can see they're flatter, much more flat than those consolidated layers that are surrounding it. So that's what I'm talking about when I say that the direction of groundwater flow also depends on the local geology conditions as well as the connection to surface hydrology, where those sediments and the direction of groundwater flow is more dictated by the geology layers that it's situated in and the connection to the surface hydrology. This map shows the old Taze River system originating here in southeast Ohio and the headwaters and flowing to the northwest across Ohio. And you can see it was part of a very large dendritic drainage system. And these old river channels that are still in our section of the unglaciated part of Ohio were filled in with the fallout and the sediments of the glacial washout. And so that's what we see. The port's facility is sitting on those glacial outwash lacustrine lake sediments that are confined by the consolidated geologic layers. Okay, so we're going to talk a little bit about the groundwater and surface water interactions. In this diagram, you can see what we have is our aquifers. An aquifer is a water-bearing rock that has high permeability and is usually found in our unconsolidated geologic layers. Here you can see an unconfined aquifer close to the surface with our surface stream hydrology there, and then a confined aquifer that's separated by an impermeable geologic layer. Confined aquifers are usually deeper, they're under more pressure, their regional groundwater recharge is usually from farther away, where your unconfined aquifers have more of an interaction with what is occurring on the surface. Your recharge is much quicker, you have more connection to the surface hydrology, and there's more of an exchange with a less period of time in our unconfined aquifers. Here we see the saturated versus the unsaturated zones. When we talk about groundwater, that water in its infiltration period is going to move through some soil matrix where you have pore spaces that are partially filled with water and partially filled with air. And that's what we call our vadose zone. That's the unsaturated zone. And then once you hit the saturated zone, the phreatic zone, you see the water table line. All the pore spaces are filled with water at that point. And your compounds or your chemicals movements flow differently, whether it's in the unsaturated zone or the saturated zone. Okay, so when we talk about groundwater recharge, this slide demonstrates what I was talking about earlier, where the unconfined aquifers often have a quicker recharge to the surface hydrology. In this diagram, the stream. If you notice where the day marker is, if a pollutant was spilled on the surface there, it could reach that stream within a couple days. The further you are away from your surface hydrology, the longer it would take. But you could see some of the confined aquifers that are much deeper, chemicals that migrate and infiltrate much deeper down sometimes take centuries to millennia to actually reach that surface hydrology. And in this case, our geology is flat, but if you could imagine these geology layers at a certain dip, that would mean that the contaminants could be flowing even for a longer period of time along that those geologic strata along the dip. Okay, when we pump groundwater, in this diagram you see a well situated outside a backyard. This is a very small personal well use. But you can see what we call the cone of depression or the drawdown that we see with our water table near well sites. So as water is pulled up through that the well bore, you're going to pull out you're going to have a drawdown of the water table to that, like a straw. You're sucking that water up from the water table, and it's going to pull down the cone of depression of that water, the edge of that water table. This sometimes can be very useful in situations where you're trying to pull a contaminant out of the water. You can use a pumping scenario where that chemical could be pulled through the water table and up through that well. And so you can have a reverse recharge situation, like for this stream where the natural recharge would be going into that stream. You're actually pulling water out of that stream up through that pumping scenario for this situation.
I'm Dr. Natalie Cruz. I also work for the Voinovich School of Leadership and Public Affairs, and I'm going to continue where Jen left off, talking about groundwater pollution and groundwater modeling. So Jen spoke to you a little bit about the unsaturated zone and the saturated zone. So what you can see here is, in a case where you have a leaking source or a leaking tank or barrels on the surface, that pollution can migrate downwards through the unsaturated zone and through time can advance into the saturated zone and flow down dip towards a receptor. So in this case, you can see on the far left of the slide a city water well, but the treatment facility intercepts the pollution before it reaches a receptor. So when we think about groundwater pollution, we usually visualize it as a plume. So what you can see here is this pink plume of contaminant going from a leaking underground storage tank through the saturated groundwater flow and spreading out until it gets to a discharge point of groundwater. So as Jen spoke about, groundwater interacts with surface water and ends up reaching a river or a stream as a discharge point at some point. And so what you can see here is a groundwater plume spreading out and eventually making it to a stream. So this is pretty simple to visualize in 2D, but when we start thinking about groundwater plumes in 3D, what we have to realize is that the geology varies as we go out from a single location. And so what's typically done is a series of monitoring wells are used to determine the concentration of a contaminant in the groundwater over an area, and that's then used to visualize how a plume is situated in 3D. So what you can see here is a 3D rendering of a contaminant moving through the groundwater, and what you can see is that it looks a little bit more complicated than the situation I showed you in 2D. So with that monitoring data, what you can do is create lines of equal concentration of a groundwater contaminant or an isopleth. So what you can see here are all these black dots that are locations of monitoring wells, and from those monitoring wells they have analyses that determine the concentration of TCE in this case in the groundwater. And from that they've created what looks like almost a topographic map, but in this case it's a map of concentration of TCE in the groundwater. And you can see how it spreads out from the source in the Eastgate disposal yard and flows down dip, down groundwater flow towards the lake, which would be a receptor. So this is a case study from Washington State that kind of visualizes how we look at that concentration. It's a pretty simple picture right there, but when we start thinking about that in 3D, what we have to realize is that the geology varies as we go down into the earth. And so there are places with higher or lower porosity or varying dip at a specific location, which is going to change how that groundwater contamination moves. And so what you can see here is that from that very simple picture on the surface or looking down at that plume is a much more complex picture when we look in 3D. So because there's a lot of complexity behind how groundwater moves and the geology, we use groundwater models to simulate how groundwater moves in the subsurface to try to simplify, but also to try to project into the future. So we use geologic measurements and groundwater measurements, looking at real measurements of contaminant concentrations and groundwater level and groundwater movement to simulate how groundwater behaves with a computer model. And so we use that not only to explain current conditions and what's happening now, but then you can also project into the future and model future conditions to start making cleanup decisions. And this is what's happening at the Portsmouth Gaseous Diffusion Plant. Cleanup decisions are made based on RCRA, or the Resource Conservation and Recovery Act, through consent decrees with the state and federal government. And what this includes is an assessment of the site and a description of current conditions, and from that, an investigation to figure out the removal and containment and treatment options in terms of our cleanup alternatives. And groundwater modeling has a central role to this at ports. Types of remedial action that can be undertaken under RCRA include removal of contaminated material, containment of contaminated material, and treatment of contaminated water. So when I talk about removal, typically what that means is that we remove contaminated soil. So contaminated soil or surface material can contaminate the groundwater when precipitation picks up that contamination and infiltrates down into the groundwater table. So by removing the contaminated soil, you can remove the source of the groundwater pollution. We can also remove the contaminated water or pump the water out of the plume in the subsurface. So what you see here is a diagram of a pump and treat system where a groundwater plume is being extracted from wells. You can see the cone of depression drawing groundwater towards those wells, and that contaminated water is extracted through extraction wells. It's then treated to discharge requirements and discharged into surface water. Another option for dealing with contaminated material is containment, and typically what we mean when we talk about containment is containing it in a RCRA landfill. So by removing contaminated soil, you then need to put it somewhere, and so typically a certified landfill would be the option for disposal and containment. You can also try to contain groundwater pollution in the subsurface with barrier walls. So a barrier wall would be a slurry wall, which would typically be a clay material that doesn't transmit water very well, that would be cut into or keyed into the bedrock and capped at the surface. And the purpose of that would be to try to stop groundwater from flowing past that point. And so by putting a barrier wall in down dip of a plume, you may be able to arrest the movement or the flow of that plume past the point where you don't want it to go. So what you can see in these pictures are some examples of installation of barrier walls. In terms of treatment, there are several different options. You can inject a chemical into the subsurface to treat the plume in situ. You can have a surface treatment facility that you treat water that's pumped out of the ground in, or use bioremediation. One potential solution is phytoremediation. This has been used at the port site. So in this case, you'd have trees or plants that are planted in order to extract contaminated water. And at the end of their lifetime, they would typically be cut down and landfilled. You can also use different types of compounds injected into the subsurface to break down a chemical and remediate that groundwater contamination. So for TCE, some of the possibilities, or for chlorinated solvents, some of the possibilities are hydrogen release compounds that are specifically designed for the treatment of chlorinated solvents in the groundwater, or injection of an oxidant. So both of those options would be in situ treatment, where you're injecting a treatment medium, either a hydrogen release compound or an oxidant, into the groundwater, into a groundwater plume to break down that contamination. As part of a grant to Ohio University from the U.S. Department of Energy, we've been able to work with the current conditions groundwater model created for the port's site that's going to be used to create a future conditions model that will be used to make cleanup decisions at the site. As part of this project, we've been a third-party reviewer to make recommendations for future conditions modeling based on our experience in groundwater modeling. We've also been able to use the site-wide current conditions model to look at groundwater surface water interaction, to look at transport of inorganic pollutants, and to look at interaction between on-site groundwater and off-site wells. Through this work, we've been able to show that there are very few conditions in which contamination would move off-site, which is a very positive thing for the decommissioning and decontamination of the port site, and have shown that the current treatment systems are working very well at managing the groundwater pollution on the port site. This project had 3 deliverables that are all available at www.portsfuture.com: a groundwater regulatory requirement review, a site-wide groundwater model review, and an application of the site-wide groundwater model, all for the port site in Piketon, Ohio. For more information or to get copies of the reports, you can go to www.portsfuture.com. Thank you so much for your attention.